Stand at the edge of the ocean on a winter day in, say, northern Norway or coastal Alaska. The air is well below freezing. Your breath clouds instantly. The ground is frozen solid. A puddle near your feet locked up days ago. And right there in front of you, the ocean is still moving. Waves rising and falling, the surface glittering, completely, stubbornly liquid. That should strike you as strange. Fresh water freezes at 0 degrees Celsius. Air temperatures in the Arctic regularly hit -20, -30, sometimes -40. That is cold enough to freeze almost anything. A glass of water left outside would be solid in minutes. Lakes go opaque, rivers crust over. And yet the ocean, this vast ancient thing, just keeps going. Why? The obvious answer is salt. Everybody sort of knows that. Seawater is salty, salt lowers the freezing point, ocean doesn't freeze. Simple. Except it isn't. Not even close. Yes, dissolved salt does lower seawater's freezing point. And here's the part that should stop you. It lowers it by about 2 degrees. The freezing point of typical seawater sits around -1.8 degrees Celsius. That is it. 2 degrees of buffer between ocean water and the freezing point of a regular glass of water. Meanwhile, Arctic air is sitting at -30. Salt chemistry alone would have lost that fight before breakfast. So something else is going on. Several something else's, actually. All running at the same time, all interlocking in ways that are far more impressive than a little chemistry. The first thing to understand is that the ocean is not passive. It is not a giant bathtub sitting in the cold, slowly losing heat until it finally surrenders. It is a system that actively moves heat around, and it has been doing that for longer than humans have existed. Think about how a lake freezes. Cold air chills the surface layer. That surface water gets colder, and here's the key thing. Fresh water is at its densest at 4 degrees Celsius. So as the surface cools toward 4 degrees, it gets heavier and sinks, mixing with warmer water below. But once the surface drops below 4 degrees, something changes. Now the colder water is actually lighter than the water beneath it. It stops sinking. It floats at the top, keeps cooling, and eventually locks into ice. That ice layer then acts as an insulating lid, protecting the deeper water beneath it. That is why lakes freeze from the top down, and why fish survive winter in lakes. There is liquid water trapped below the ice. Salt water does not work like that. Salt water gets denser the colder it gets, all the way down to its freezing point. There is no reversal, no point where the cold surface water suddenly becomes lighter and stops sinking. So when polar ocean water cools at the surface, it gets heavier, sinks, and warmer water from below rises to replace it. The ocean is constantly pulling its own cold surface water away before it gets cold enough to freeze, and replacing it with water that has to start the process all over again. The ocean is not losing a slow battle against winter. It is running an active defense, and that defense is built into the physics of salt water itself. But that is still just one layer. The ocean is also running a planetary heating system that most people have heard of but probably underestimated. The thermohaline circulation, sometimes called the ocean conveyor belt, is a global network of currents driven by differences in water temperature and salinity. Warm water from the tropics moves poleward through currents like the Gulf Stream. That warm Atlantic water flows up into the North Atlantic and keeps places like Iceland and the coast of southern Greenland largely free of sea ice year-round, despite their latitude, despite their winters. Think about that for a moment. Iceland sits just below the Arctic Circle. Its winters are brutal, and yet its ports stay open, largely because a slow river of warm tropical water is flowing toward it through the ocean, all the time, constantly, like a heating system that never switches off. This is not a local effect. It is planetary. The conveyor belt connects every major ocean basin. It takes roughly 1,000 years for water to complete a full circuit, and the whole time it is redistributing heat, pulling warmth away from the tropics and delivering it to the poles, moderating the most extreme cold, and keeping polar oceans from freezing over completely. Now here is where it gets genuinely strange. When seawater does begin to freeze, when conditions get cold enough and the defense starts to slip, something happens at the molecular level that changes everything. Ice crystals have a very specific geometric structure. Hydrogen and oxygen atoms locking into a rigid, repeating lattice. And salt ions do not fit that lattice. There is simply no room for them. So as ice crystals form at the surface, they physically eject the dissolved salt back into the water beneath them. What does that do? It makes the surrounding water saltier. And saltier water is denser water, and denser water sinks. And sinking cold, salty water is exactly what drives the thermohaline circulation in the first place. The very act of the ocean beginning to freeze is what powers the conveyor belt that pumps warm water back toward the poles. Harder to freeze and triggers the circulation system that brings warmth back to the region. The ocean freezing is self-defeating. Every time ice tries to form, it makes the remaining water negative feedback loop built directly into the chemistry of ice formation. The ocean does not just resist freezing, it uses the attempt to freeze as fuel to prevent more freezing. This is also why the icebergs and glaciers you picture when you think of polar ice are not what you might assume. They are not frozen ocean water. They are frozen fresh water. Snow that fell on land, compacted over centuries into glaciers, and eventually crept into the sea as ice shelves that calved into floating bergs. Real frozen ocean water, sea ice, is thin, flat, and relatively young. It forms slowly in thin sheets, starting as tiny needle-like crystals called frazzle. And because the salt keeps getting expelled as it forms, sea ice is mostly freshwater ice floating on an ocean that has become slightly saltier because of it. 4 mechanisms, all running simultaneously. Salt chemistry pushing the freezing point lower, density physics pulling cold surface water away before it can lock up. A planetary conveyor belt delivering warm water from the tropics without pause, and a brine rejection loop that turns the first signs of freezing into the engine that prevents more freezing. Pull any one of those out, and the polar ocean looks very different. If you removed the salt entirely, kept everything else the same currents, same volume, same depth, the surface physics would flip. Cold water would stop sinking. A cold, light layer would sit at the top and freeze, just like a lake. Then that ice lid would insulate the water below, and the conveyor belt would gradually lose its saltwater engine. The system would unravel. The polar oceans, without their salt, would likely be frozen solid. The saltiness is not a detail. It is the architecture. So go back to that winter coastline. The air well below zero, the ground locked up, and right there in front of you, the ocean still moving, still dark, still stubbornly refusing to surrender. What you are watching is not a body of water that happens to be salty. You are watching 4 interlocking physical systems, molecular, local, and planetary, all running at once, all reinforcing each other, all fighting winter at the same time. And when a thin crust of sea ice does form at the poles, it is not the ocean losing. It is the ocean making the water beneath it saltier, denser, and harder to freeze, and feeding the very circulation that will eventually push warm water back in. The ocean is not passive. It never was. It is engineered by physics to resist.